Hello everybody, it's Abba, and I want to make a small video here to talk about the music matrices spoken about in section 6.10 of our course textbook. And there is an exercise that was not assigned called 6.10.13, and it asks the following: for all the musical matrices that we have calculated, the diagonal values from the top left to the bottom right are always some constant value. So we can kind of see that in matrices like the following. On the diagonal we have all sevens. Okay, for instance. So I'm not assigning this problem because it's an odd problem, so the solution's in the back. In fact, there's a small error in the solution, so if you do look at this solution, there's the errata of the book on Dr. Walker's website where you can see the correction of the solution. But instead of that, I kind of want to just give an example of how to run this new algorithm. It's a lot. I personally, and Dr. Walker agrees, that it's a little bit easier than the matrix algorithm described on page 246. So let's just do an example. Before we do the example though, let's talk about some kind of basics. What are we dealing with here? We have the pitch class transformation group, map, that's a C in factor, C, a sub 12, where we have 12 pitch classes, 0 to 11. You can view those as the notes on the chromatic clock, for instance. There's 48 elements in this group. These elements are called transformations. So we have the transpositions, we have the inversions, capital I, we have the retrograde transpositions, and the retrograde inversions. And since there are 12 of each of these, that's 48 total. But in this example, we're going to limit ourselves to the set S, where our set S only has the values 0, 3, 6, and 9. So now these subscripts then will always be 0, 3, 6, and 9 also. So that gives us 16 transformations of the 48. So 1/4 of these elements are given when we limit our pitches to these classes here. And I represent them here on the chromatic clock. We have C, D sharp, F sharp, and A at the numbers, pitch classes 0, 3, 6, and 9 respectively. Okay, so let's show this method of how to get this matrix down. Okay, so if we think about, some more space. So we have the numbers 0, 3, 6, and 9, and we're going to consider initial row of 3096. So we have 3096, so going counterclockwise, starting at 3 o'clock. Okay, so we have 3096. So if I don't transpose at all, 3 stays 3, 0 stays 0, 9 stays 9, 6 stays 6. And then up here we'll have the inversion in this column. So if we do believe that the 3's will always be on the diagonal, actually it might help if I do this. Okay, it's no longer a matrix. I know if I start drawing all these lines here, but I think it'll make it easier. So our matrix is this 4x4. I'm highlighting it. So that's our 4x4 matrix in the pink box. Okay, so now, if we do believe that there's 3's everywhere on the diagonal, so the action of these transformations, these 16 transformations when the subscript is 0, 3, 6, or 9, is acting on this initial row. So I want to know what I'm transposing 3096 to this row. So what is the subscript here? So what do I have to raise this thing to get that value? Well, we have actually I think with my fan on, you might be getting some, I'll be hot just for a minute. Okay. Sorry, with the fan on, that kind of sucks. Sorry about that. So I want to know, what do I need to add to this to get the next row? Well, we have a hint. Since a 3 is forced to be here, I must add 3 to our pitch class 0. So this must be T3. That's forced, just because a 0 transposes to 3. So I add 3 to 3, we have 6. Add 3 to 9, that's 12. But mod 12, this becomes 0. Add 3 to 6, we have 9. So now we look at this 3. What is the subscript on this transposition? Remember, we're always acting on this initial row. So how did I get from 9 to 3? Well, to get from 9 to 3, I have to add 6, because 9 plus 6 is 15, and 15 is the same as 3 mod 12. So I have to add 6 to 9 to get the 3. I add 6 to this 3, I get a 9 here. I add 6 to this 0, I get a 6 here. I add 6 to this 6, I have 12, but 12 is 0. Now lastly, what do I need to transpose to get from 6 to 3? Well, we have to, well, clearly it's subtract 3, but that's the same as adding 9. So I have to add 9 to 6. If I add 9 to 6, I get 15, which is our 3. So this must be T9. So if I add 9 to the 3 here, I get 12, which is 0. I add 9 to the 0 here, I get 9. I add 9 to the 9 here, I get 18, but 18 is the same as 6. So we have our row labels. But now, reading right to left, this must be the retrograde transformation T0. This is the retrograde transformation of T3. This here is the retrograde transformation of T6. And this is the retrograde transformation of T9. Cool. So we have our row labels. So now let's think about our column labels. So this is where this algorithm gets really groovy. We want to know, what inversion is this? I sub what? Well, one easy way to think about this is to think about, what do I need to get? How do I get from 3 to 0? Well, you can subtract 3, but that's the same as adding 9. So that makes a 9 here. And we'll verify that in, after this for a second. But let's say, so if I take I9 and I act on the initial row, these 4 values, I get these 4 values. So what is the subscript on this one? Well, what do I have to add to 3 to get 9? Well, that's a 6, so that puts a 6 here. Similar here, what do I have to add to 3 to get 6? I get a 3, so I have I3 here. And then, of course, the retrograde labels. We have retrograde inversion here, and then the retrograde inversion Ri9, and then retrograde inversion Ri6, and then lastly, retrograde inversion Ri3. So that's where we got, that's the simple way to construct the new musical matrix. But let's kind of verify something, just because it seems kind of like abstract a little bit here. Let's think about this I9. Now I9 is the shorthand for the chromatic pitch class chromatic inversion I sub tj. And for every I sub tj, question 2 in your homework that's due for exercise set 5 says there's a correspondence between these pitch class chromatic inversions and these inversions curly I sub k, that we can solve for k as some function of j and some pitch class. And that's their homework problem, so I won't do that for now. But what I will do is consider if this is actually correct. Like, is I9 of 0369, does that give us this, sorry, whoops, my bad, of the initial row, it's always the initial row that we're acting on, 3096, does this give us 0369? Well, if our correspondence is correct, it's clear that I9 of 3 is I sub curly something of I sub curly k of the value 3. So what is my k supposed to be here? Well, our k, we know that according to this, I sub 9 of 3 is 0. So this is 0. So I sub k of 3 is equal to 0. Let's go back to what the formula for I sub k is. I sub k of m is k minus m. curly I sub k, that is. So if I said that, if I have curly I sub k of 3, and I know this equals 0, and this has to be k minus 3, k minus my m value, pitch class, which is 3. So what is our k forced to be? Our k has to be 3. So this k is 3. So this is curly I sub 3 of 3. So what this is saying is that this I sub 9 is really curly I sub 3. And curly I sub 3 says, take our pitch class and take 3 minus that thing. So this number should be 3 minus 0. That's the number here. This number here should be 3 minus this 0, which is 3. This number here should be 3 minus 9. 3 minus 9 is negative 6, but negative 6 mod 12 is positive 6. And this number here is 3 minus 9, and 3 minus 9 is negative 6, but negative 6 is positive 6. So we're good. So we, sorry, I think I just misspoke for a second. No, I said that correct, yes. That's it. That's all I want to say. The video got a little longer. Really, I could have stopped. I didn't need to talk about that. I just wanted to talk about this alternate method by putting this number in the diagonal. You can quickly make this matrix without using the algorithm on page 246. And that's me done. Bye. Peace.